A distance time graph in physics helps us to plot or graphically represent how the position or distance of an object keeps changing with respect to time. So in this video, I'm actually going to teach you how to really do that, as simple as possible. So our subject of consideration is going to be the guy in green. We are going to check how his movement or his position keeps changing with respect to time and see how to plot it on a distance time graph. So we are actually going to monitor his movement using this table. We will check the time he spends in each phase of his movement and the distance he covers at each level. So we are starting at this place, the starting point. So this is his starting point. The distance he has covered so far is 0 meters, and then since he hasn't covered any distance at all, we assume his time is also 0 seconds. Now what happens is, he then moves from this point to this, and this is what happens. The distance he has actually covered in moving from his starting point to this point is 12 meters. So the interval, the distance between this, that is the distance from here to this, is 12 meters. And how long did it take him to move from his starting point to his new location? It took him 4 seconds, so in 4 seconds he covered 12 meters. And here's the interesting thing. After covering 12 meters, he stopped moving. He stood at his new position for 5 seconds. So if he stopped at his new location for 5 seconds, all that means is that he's not moving at all. So the distance covered in that 5 seconds is 0 meters. So to recap, he walked for 4 seconds covering 12 meters and stopped to talk to this young lady for 5 seconds without moving. After saying whatever he wants to say to the young lady, she then turns and leaves him alone. So he has no other option than to continue his journey. He then moves from his new location to this place. Now the distance from his first stopping point to his new location is 10 meters. He moved from his first stopping point to his new location, and the distance he covered in doing that is 10 meters. And how long did it take him to cover the 10 meters? It took him 3 seconds. Now after getting to his new location, what he did again is to stop and spend just 2 seconds over there. So if he stood there for 2 seconds, it's obvious he wasn't moving. So the distance he has covered in that 2 seconds is 0 meters. So far, we've made an interesting progress. He started at his starting point, covering no distance in 0 seconds. He then moved from the starting point and stopped with the first lady after covering a distance of 12 meters in 4 seconds. He then stopped and stood with the girl for 5 seconds. During the 5 seconds, he covered no distance at all. After that, he walked to his current location, and the distance covered was 10 meters. He covered that distance in just 3 seconds. Then he stopped again for 2 seconds, covering 0 meters. Now, after having a conversation with his friend in blue, he then turns back and returns to his starting point. It took him 6 seconds in returning to his starting point. So this is a narration of his movement from his starting point back to the starting point. Now we are to represent this on a distance time graph. How do we do that? For every graph, we need a vertical and a horizontal axis. After getting our axis drawn out, we need to indicate what each of them stands for. For our scenario, we are going to draw distance moved against time taken. So the vertical axis stands for distance in meters, and the horizontal stands for time in seconds. Each of them has a starting point of 0. On our time scale, we are going to represent each interval with 2 seconds, meaning each interval stands for 2 seconds. So we have 2 seconds, 4 seconds, all the way to 24 seconds. On the distance scale, each interval stands for 4 meters. So we have 4 meters all the way to 28 meters. Note that the scale you choose depends on the values you have. Now it's time to plot. To make the plotting easy for us, I've added some guidelines to help us. Let's start by picking our first pair of values. For 0 seconds, the distance covered is 0. This is where it is located on the graph. Let's indicate it using this red dot. Now for our next points, he covered 12 meters in 4 seconds. This is where that is located on the graph. Now all we have to do is to connect the 2 points. So this is what we have so far. He started from rest, that is the starting point. He then walked for 4 seconds covering 12 meters. After covering these 12 meters, he stood there without moving for 5 seconds. Note that if he stands for 5 seconds, what that means is that he has already spent a total of 9 seconds in his journey. Also, 5 seconds of those 9 seconds were spent standing, meaning time kept moving for those 5 seconds, but his distance remained the same. This portion of the graph is represented using a horizontal line. So far, he has covered a total distance of 12 meters in 9 seconds. I hope you got that. Leave a comment in the comment section below if you're on track with us. Now for our next set of points, he moved a distance of 10 meters in 3 seconds. So 10 meters added to his current distance covered will give us 22 meters. Meanwhile, it took him 3 seconds in covering the 10 meters. So adding the 3 seconds to the time he has already spent in his journey gives us 12 seconds. After covering this distance, he then stopped again at the 22 meters mark. And how long did he spend there without moving? He spent 2 seconds. So his time has now moved to 14 seconds. So far, he has spent a total of 14 seconds covering 22 meters. Now, after standing for 2 seconds with his friend in blue, he then turned and moved back to his starting point in 6 seconds. This is how that is represented on the distance time graph. A distance time graph visually represents an object's motion over time, with time on the x-axis and distance on the y-axis. The plotted line indicates changes in distance, revealing key details about the object's movement. Inclined lines in the graph signify motion. An upward sloping line shows that the object is moving away from its starting point, meaning its distance is increasing as time progresses. Conversely, a downward sloping line represents the object returning toward its initial position, indicating decreasing distance. The steepness of these slopes determines the speed. Steeper lines correspond to higher speeds. In the given graph, the object moves away from the starting position between 0 seconds and 4 seconds, then again between 9 seconds and 12 seconds, before reversing direction and returning to the start from 14 seconds to 20 seconds. On the other hand, horizontal lines represent stationary periods where the object remains at a constant distance while time continues to pass. This means the object is at rest during these intervals. In the graph, the object stops moving between 4 seconds and 9 seconds, and again briefly between 12 seconds and 14 seconds, maintaining the same position before resuming motion. Overall, a distance time graph provides crucial insights into motion, including when an object is moving, stopping, or changing direction. Inclined lines indicate motion, horizontal lines indicate rest, and the steepness of slopes represents speed. This makes distance time graphs essential tools in physics for analyzing movement patterns and understanding kinematics. There are actually other vital information we can get from distance time graphs, but in order to do that, we are going to track the movements of these two balls on this 24-meter track. Let's see how long it takes for each of them to complete their journey. It took the black ball 6 seconds, but for the red one, it took 14 seconds to complete the journey. Let's plot the movement of these balls on the same distance time graph and see the difference. The black ball covered a distance of 24 meters in 6 seconds. The red covered the same 24 meters in 14 seconds. From the graph, it is obvious the line representing the black ball is steeper than that representing the red. What does this mean in distance time graphs? The steeper the line, the faster the movement. A distance time graph provides crucial insights into an object's motion, revealing whether its speed is constant, increasing, or decreasing. The 3 graphs presented illustrate different motion patterns based on the shape of the plotted lines. In the first graph, the straight diagonal line represents uniform motion, where the object moves at a constant speed. Since the distance increases uniformly over time, the speed remains unchanged, meaning there is no acceleration or deceleration. This type of motion is typical of objects moving at a steady velocity, such as a car cruising at a constant speed on a straight road. The second graph, which shows a curved line bending inward, indicates deceleration or negative acceleration. Here, the object's speed gradually decreases over time, meaning it covers less distance per unit of time. This motion occurs in situations like a rolling ball, slowing down due to friction, or a vehicle coming to a stop after applying brakes. The curvature signifies that as time progresses, the object moves increasingly slower until it eventually stops. In contrast, the third graph features a curved line bending outward, representing acceleration. In this case, the object's speed increases over time, meaning it covers more distance per unit of time as it moves. This is seen in scenarios such as a car speeding up after a stop, a free-falling object gaining velocity due to gravity, or a rocket launching into space. The steeper the curve becomes, the greater the acceleration. Overall, these three graphs highlight the fundamental types of motion: a straight line for constant speed, an inward curve for deceleration, and an outward curve for acceleration. Understanding these motion patterns is essential in physics, engineering, and real-world applications like vehicle dynamics, sports performance analysis, and aerospace technology. So this brings us to the end of our interesting lesson on distance-time graph. To conclude, I have a question for you. If two objects start from the same point, but one has a steeper slope on a distance-time graph, what does that tell us about their motion? Can you think of real-life scenarios where this happens? Finally, what new insight have you learned from this lesson? Write your answers in the comments section below. Give this video a like and subscribe to our channel. See you in our next lesson.